Yeah. I give up now. I'm almost finished. Okay, but we did this for I probably get far away from that.
Do you want any better one?
So can we move our attention here forward, please? How the complement works, I keep the same vertices. Every time there's an edge AB, I don't put an edge. Every time it's not an edge AE, I put it here. So what else do I have? I have BC, I have AD, right? What else? From B, I have BE. I don't have AB, I have BC, I have BD. No, no BD. How about C? CD, I have CD. CE? No, CB, I have that. And how about D? I have DA, and I have D, C, and that's good, right? So, very simple mechanical procedure. Now, how about I'm adding here something. Here's the complete graph. Complete means what?
All edges are
All edges, right? So that's all edges in. A, B, C, D. Again, this is not new stuff. This is just recap to make sure we said everything, just in case some of you don't know what the complement graph is. My point of this is that this has all edges, and we already said how many edges are there. If we have n vertices in a complete graph, has how many edges? Complete. And choose 2, we don't know what that is yet, so keep that thought. We just computed that differently, not with n choose 2. We just, remember the number? All right. So we can do that count without the notion of combinations, n choose 2. We said you go through all vertices, every vertex has degree exactly, n minus 1, right? You multiply by n to get the total number of incident points, so you get this. And then you have divide by 2 because every edge has been counted twice, right? We don't need an n choose 2 yet to do that. Yes?
So if we were going to use this fact in the proof, would we have to state all the logic of how we got times?
No. We prove something in class, you can say, I proved this in class, I don't need to prove this again. Right? You should state where you got it. This is from the textbook, this is from the recitation exercise, this is from the class, this is from my friend, he told me that. No, that's not, you can't take that. Right? Okay, here's my point about complements. Every single edge in the complete graph must be exactly either in G or in G complement. So whatever, any single edge in here is got to be either there or there. It cannot be in both, and it cannot be missing in both. Hi. Somebody call it for me? Yeah. Can you turn the projector off, please? We don't want to interrupt the lecture. If you cannot, you cannot. We trade this button here, and nothing happens. So we'll keep doing the lecture. He'll try to turn the projector off. If maybe he succeeds, maybe not. All right. It seems to be warming up. Is that clear? Every single edge must be either here or here. So I think that's related to one of the problems you have in this homework. So let's do another example. If question?
What is this below the complete graph? What is that saying?
Has this number here?
Yeah.
This is a notation. This is called n choose 2. And you don't have to worry about it now because we're going to talk about it on Friday. But n choose 2, which is a number, it's really n times n minus 1 by 2. So if n is, in this case, what's my n here? 5? And this will be, for n equal 5, will be 5 times 4 divided by 2. How many edges is that? Success. No? Yes. No. Well, so 10 edges. This is 10 edges. How many are in here? How many are in here? Right. So how about take another example to clarify this maybe better. I have now 6. Right? So here's a graph with 6 nodes, and I have some edges here. I'm going to draw these triangles, 2 triangles. So this is really 2 disconnected components, right? I draw it intersecting, but if I don't mark these intersections, I'm really having 2 triangles which are 2 separate components, A, B, C, D, E, F. So if I draw the complement, A, B, C, D, E, F, right? I don't want to draw the full graph, but I can compute the number. If n equals 6, number of edges is n times n minus 1 by 2. How much is that? 6 times 5 by 2. How many edges are here? 15. So if this guy had how many edges? 6. How many edges will be in the other one? Must be 9. Because all the edges that are missing from here are showing up in there. Which ones? AB is an edge. AC is an edge in here. How about AD? No. AE? AF?
Yeah.
Yes. From B, BC is not an edge. BD?
Yes.
BE?
Yes.
And BF? No. So from C now, I get CD? CE? CF? No. And CA? Yes, I already got it. Thank you. How about from D? DE is an edge, no, DF. DF in here. From E to get EF. How many edges I got so far? I'm missing one?
No, you're good.
I got 9?
That's 9.
So that's the story with complement graphs. And there's one more thing. I think everybody figured that out by now. I don't need to write on the board. What's a C cycle or K cycle? If I have a 7 cycle, what is that? What kind of graph is a 7 cycle?
Graph with 7 vertices.
And a cycle.
Yeah.
Right. So this is a 7 cycle. 1, 2, 3, 4, 5, 6, 7. 7 cycles. So that's a graph. It says that's all the vertices and that's all the edges, and the edges that you don't see are not there. Yes?
Can we still consider it a 7 cycle if there is an additional connection between 2 of the nodes in that cycle?
No. You can say the 7 cycle is a subgraph of that graph because it has more edges, but I take some out. If you just say a 7 cycle, that's a 7 cycle. A 4 cycle is just a square, right? That's a 4 cycle. It's just a name. I could have called it, a graph with 4 vertices, A, B, C, D, and with the edges A, B, B, C, C, D, and D, A. Yes?
Are these cycles defined by their vertices, or can we define it by the number of edges as well?
You can define it any way you want, as long as you have that many vertices exact, which also means that many edges. Every 7 cycle by vertices will have 7 edges, and every 4 cycle by vertices will have 4 edges. Now, as long as it looks like that, even if not drawn like that. Like you see, this one here is actually a cycle. I just drawn it, not looking like a nice cycle. But because I didn't mark this intersection, there's nothing to do with this. So the very interesting problem, which relate in fact to a lot of reality problems like geography, which had to do with how can you draw and color graphs. So if you go a little bit into graph theory, that's the first thing you do that we don't do in this class. Which kind of graphs can I draw in a way that edges don't intersect? And which kind of graphs I cannot draw that way? Those are called the planar graphs. Okay. So this one I could have drawn differently such that the edges don't intersect. But certain graphs you can't. No matter how hard you try, you gotta have edge intersecting each other. So that being said, I'm gonna pose a problem here, and maybe we solve it by the end of the course today, related to this. Here's my problem. I have 6 people, and they reciprocal friendships. Reciprocal friendships. That's an edge. So here's my 6 people. A, B, C, D, E, F. I don't know who's friend with who. So this is just, I have 6 people and they have friendships. They're undirected. Reciprocal means undirected. If I'm your friend, you are my friend. Of course, let's assume, let's say if AB is an edge, that's a friendship. And in the complement graph, AB is not an edge, right? Because that's an edge in there, it's not an edge on the other side. On the other hand, let's say CD, there's no edge here, no edge. Then in the CD, we have an edge here, CD, edge. We call these edges friendship. So being, you are either friends with somebody, if it's a reciprocal friendship, you have an edge. And you are estranged with someone if you're not a friend. So estranged means edge here. This is a friendship. This is a friendship. It's an edge in the complement graph, which means not a friend in the direct graph. The problem states that no matter who's friends with who, either one of these graphs contains a clique of size 3. What that means, that either 3 friends, all connected, a clique, remember a clique, what it is? Clique is everybody's connected to everybody. So what the problem asks you to show, there's either a clique of 3 friends, clique again, everybody knows everyone, or a clique of 3 strangers. In other words, either there is a triangle in this graph that indicates the clique of 3, or there's a triangle in this graph which indicates a friendship of 3. Clique friendship of 3. Why is that true for any 6 people? No matter who's friends with who, there's always possible. This is a more general property of graphs, but it's instantiated here for 6 vertices. So we're gonna, you guys have until the end of the lectures to try to solve this problem. Show that no matter how you put the friendships, you either get that or that. And by the end, we'll try to come up with a solution. All right? If you have an answer, I'll ask again for it at the end of the lecture, not now. That's all I have to say about graphs. We need to move into other things. We are behind. The other sections are more advanced into the next module, which is sets and counting. So they think. Because what they did in 2 lectures, we're going to do in half an hour. So we're going to be at the end of this lecture more advanced than they are. Okay? Because lectures about sets, you guys already know sets, right? We don't have to worry too much about sets. So we already talked about sets. I don't know if you noticed, right? We said things like, who's n? N is a set of natural numbers. We put an additional bar somewhere. I think some people put a bar here, some other people, whatever. There's an additional bar in there. And what was that? Natural numbers. 0, 1, 2, 3, so on and so forth. These numbers in mathematics are sometimes axiomatic. Yeah, are the counts, the natural counts. How many ships can I have? Well, one of these numbers, you either have no ships or 1 ship or 2 ships, right? So people have identified those counts even before there was a system of numeration. Even before those numbers existed, those are Arabic notation, like Romans have different numbers. People, merchants have identified how many things you have. That's where those numbers come from. And then we talked already about this other one, which is these ones, 0, 1, 2, the counts, 3, so on and so forth, but also goes to the other side, the debts, how many ships I owe to the other person. Right? -1, -2, -3, easy. One set that you've seen before, but we didn't talk about it yet, is this one. There's different ways to put the bars here. Q, where you need another bar because this is an important set in mathematics, not just a simple Q with Q with additional bar. What is this? Rational numbers. Okay. Lights go down. Nice. What are the rational numbers if I'm to define them formally? So, the numbers that can be written as, yes?
Written as a fraction.
Fraction, like A divided by B. What A and B have to be? Integers, and B is not 0. So any way you divide two integers, you get the rational numbers, except if you divide by 0. Right? So it's 0, a rational number? Can I get 0 by this division?
Yeah.
Can I get 2?
Yeah.
Can I get -2?
Yeah.
Can I get any integer?
Yeah.
How? How do I get any? Somebody gives me an integer, I want a fraction that gives me that integer.
That integer over 1
Right. Can I get minus that integer?
over negative.
So I can get a lot of possibilities here, including all the integer values. But clearly I can get more values than the integers, right? There are more numbers here. There's some numbers here that are not integers. Can I get 2.5?
Yes.
How about 2.75? How about 2.755? How about anything that's like 2.75893 8? It's as long as I write it and I say that's my number. How do I get this number as a rational number, as a fraction? Is there an obvious way to say you want this number? I know a fraction that gives me this number. Yes.
Just put that number and take out the decimal and put it over like.
Right. So here I think you're saying this is 275891318, and then I have to divide by something because that's what I have. I have fractions.
Divide by a million.
Divide by 1 a bunch of zeros. How many zeros are here? I'm not asking the number. I mean, how many zeros I need in general?
The number of
How
decimal
many
places.
decimals I have, right? If I have 7 decimals, I need 7 zeros. Is 7 zeros a million or more or less?
10 million.
10 million. Very good. So anything that can be written with dot point decimals, it's an obvious rational number. You just write out the dot and divide by 1, follow how many zeros you need to move the dot, and you get a rational number. Since I'm here, let me make a honors parenthesis about the rational numbers. So these numbers are not dense, right? Dense, I mean common sense dense. In mathematics, there is a notion of density. We're not talking about that. Dense. They 1, 2, 3, 4, -1, right? Big space in between. If you're to draw these numbers on a line, to be here's 0, here's 1, here's 2, here's 3, here's -1, -2, -3. Obviously not dense. Between those numbers that are very discrete, there is a big gap. Right? So not dense. How about the rationals? If I'm to do the same for rational, here's a number, here's some rational, here's another rational, 2.5, here's an rational, 3.1. Are there any rationals in between? Yeah, of course. I can take those two, for example, and compute the middle one. The middle one is 2.5 plus 3.1, 5.6, 2.8, right? And how about in here? There more rationals in there?
Yeah.
Right. This is obviously dense. You can get a lot of density with those rationals. So in calculus, they have a question, how dense? Like, are they really dense? Like between, and there's no gap at all? Or can you define those gaps, right, somehow? In particular, for rational numbers, if two values are rational, their middle value, it's also rational, right? I think that's very easy to prove. That's an exercise for you that you can do. If two values are fractions, you can take the arithmetic mean and you show that's also a fraction, right? If I have someone is A1 by B1 plus A2 by B2, those are the two numbers, and I want to divide by 2. Is this a fraction? Can I write this whole thing as a fraction? There's a way here to do it. I'm sure you can figure that out. Multiply the B's with A's and add them up together. You get a division of two integers.
So if you can say that the arithmetic mean of any two rational numbers is also rational, but can't you also say that there are infinitely many irrational numbers between any two?
Irrational, as in not rational.
Yeah, between.
We didn't get that far yet. How about is there infinite number of rationals between any two? Before we get to irrationals, that is numbers that are not in Q. If there's such number. I mean, if they're very dense, maybe they're all of them, right? If they're very, very dense, why do we need other numbers? That's a different question. But for now, if I have two rational numbers, how many other rationals are in between? We need to characterize that infinity. We won't do it today, but there are many kinds of infinity. We need to express an infinity in terms of density. How dense are they? But first thing that you should notice is that this is not the same like this. These sets, n and z, don't have this property. If you sum up 2 or 3 of them and take an average, you don't get a natural number. So they have these big gaps because you can't get natural integers in between. Rationals are not just the ones in between, they're infinitely dense in between. And his question is, okay, so is any number that's not a rational, is there any value somewhere in here that is not rational? For example, can you give me an example? Yes.
Square root of 2.
Square root of 2 is not a rational number. How about pi? Not a rational number. So at some point during the recitation, either this week or next week, we'll worry about this problem, why square root of 2 is not a rational number and how many irrational numbers are there. All right. So the ones that are not rational but still on this line are what? I mean all of them, not just the transcendent one. How do we call this line? Real values, right? So it's all of them, real values, all of them. So here's something that you should have done in calculus in high school, but you probably didn't. How do you define real numbers? You can see this way I can go up to rationals, right? Natural numbers, natural counts. This is the depth, I go the other way. Q is all the fractions between integers except divide by 0. And who's R? How do you define what are the real numbers? Yes?
The union of the set of rational numbers, irrational numbers.
But we didn't define irrational, right? So he's saying everything that's on the line that's either rational or irrational is real, but we didn't define what irrational means. So this is a non-trivial problem, so to speak. You cannot come up with that definition by yourself, even if you're very smart. Somebody has to give it to you. So that's kind of something maybe we have time to get into it. How do we define those real values which are far more dense than the rational values, which are already pretty dense? Now, real values are a lot more dense. This relates to the problem of counting and the size of the sets. We're going to talk about finite sets, but infinite sets, all these sets are infinite, right, also have a size. Now that confuses a lot of people. It confused me when I heard about it the first time. Wait a minute, if all of them are infinite, how can they have different sizes? They're infinite, right? And many kinds of infinites. It turns out that those 3 sets have the same size. Even though it looks like this one has a lot more values in it, it's actually the same infinity, the same size. But this one, the real values, is not. There's more values in here. So that's where we want to go with infinite sets. But before we do, we need to talk about finite sets. Things like what the other section did for, I don't know, 300 minutes or so, 5 hours. Like, if A is the set 1, 2, 3, and B is the set A and 1. Set could be anything. It's not like we don't have to say who A is. It's just an element of B. Who's the Cartesian product A times B? I have to make pairs with the first element in A and the second element in B. And this is ordered pairs. So in a pair, it matters which one is from A and which one is from B. So this would be 1A, right? What else can I do? 1, 1. 2A. 2, 1. 3A. 3, 1. We've seen Cartesian products before? If we don't, very simple stuff. Just take all the possibilities with all the values from one set and the other values from one set. Now what I want to point out in terms of order means the pair A1 is not the same as pair 1A. And specifically we put this in round brackets typically to say that's a pair order. Now sets have no order. In other words, set A could be written as 2, 3, 1. That's exactly the same set. And that's why they have curly brackets. In curly brackets, order doesn't matter, but in round brackets, it does. Sometimes those are called pairs, but if I do 3 of them, it's a triplet. In general, it's called a sequence. A sequence has order, a set has not. That's the only difference between sequences and sets. If it's out of order or in any order, we call it a set. If the order matters, we call it a sequence.
So why is that A times B is in a
Cartesian product.
Why is it that it's 1A and you don't have A1?
Because there's no way to form a pair. The first element has to be from A, and the second element from B. So I cannot get A1 with A from the A set, and right? So how we define this formally, if we want to say in a set builder notation. Set builder notation. That would be all the pairs AB with the property that A belongs to A and B belongs to B. So I just said all the possible pairs you can make where the first element is from set A and second element is from set B. And guess what is the size of a Cartesian product? How many elements do I get in the product? Yes?
It's the size of A times the size of B.
We call this the product rule. But I want to give you an English definition for it, which is the one you should keep with you. The English definition is every possibility which is one from A, one element from set A and one element from B, every possibility or pair, let's write it as a pair with round brackets, is valid. I think that's a better definition for counting purposes. Of course, that's what it means. I have all the pairs with the first one from A and second one for B. But for counting purposes, we want this validity, yes.
What's the functional purpose of a Cartesian product? Like, why is it useful?
Oh, there's like, just a simple example in cartography, right? You have coordinates, right? You have an X coordinate, a Y coordinate. If you have a three-dimensional space, like the real space, you have an X and Y and Z. GPS is like that. Every time you need a pair of things, right? Edges were pairs of vertices, right? Every edge in a graph could be a pair of vertices. So I could multiply an A with itself. Right? I could say A times A, and I get what? 1, 1, 1, 2, 1, 3. That's this one multiplied with 1, 2, 3, and then I get 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. How about I add the set here? I add the set C is the set A to B. Again, we don't have to specify who A is and who B is. Those are elements, could be students in a set of students, could be computers in a network, could be vertices in a graph. What if I do A times B times C? Now I'm not getting pairs, I'm getting triplets, right? Has to be the first one from A, first one from B, third one from C. So those will be all A, B, C triplets. Notice that order matters in a triplet. It's not among the triplets, but in the triplet order matters. So A has to be from A, B from B, and C from the set C. So what is this set? What are all the triplets here? 1A. How do I get 1 and an A? 1A. Right? What's the next one? 1A, B, 2.
Yeah.
That's a 2 here. 1A, 2. What's the next one? 1AB. 1, 1A, 1, 1, 2, and 1, 1, B. Right? So that's not over. Now I move to 2. 2A, 2A, 2, 2AB, 2, 1A, 2, 1, 2, 2, 1B, and then I do the 3, 1, this guy, 3AA, 3A2, 3AB, 3, 1A, 3, 1, 2, and 3, 1B. You put the curly brackets, the set. Right? So the order in which I'm writing those triplets, it's the construction order, the first times the first times the first, first, second, first, third, first, second is a lexicographic construction order. But as a set, I can write them in any order. This is a set of triplets. The triplets could be written in different order as long as I get all, how many I have here? 18 of them, that's fine. So whether I put this one first or this one first or this one first doesn't matter because it's a set. But inside the triplet, whether it's 1AA or A1A, is that a difference?
Yes.
Yes. The triplets are ordered but inside, but not as part of the set. So what's the side of A, B, C here? A times B times C is size of A times size of B times size of C. So that is, of course, 3 times 2 times 3, 18. Same rule, just apply to 3 sets instead of 2 sets. So how do you think of this rule, product rule? Here's how to think about it. If I have 3 hats, 4 jackets, and 2 pants, in how many ways can I dress up? 3 times 4 times, 2 and so on and so forth, right? Because I can put any hat with any jacket, with any pants, with any shoes. So I like this definition that says you can use every hat with every jacket, with every pant, with every shoes, and all of those possibilities are valid. Like I'm counting all of them. How to generate those possibilities is literally how many of things you can get here times how many of things you can get, how many things you can get here. That's exactly what happened here. If generating those triplets goes like A, B, C this way, well, it comes down to how many ways can I choose the first element, 3, times how many ways can I choose the second element, 2, times how many ways can I choose the third element, 3, every possibility, every one of these choices independent to the other. So whatever choice I make for the first element goes with every choice for the second, goes with every choice for the third. So every choice generates a new possibility. Therefore, I have 3 times 2 times 3 number of possibilities. That is the product rule. Quick example. Suppose I have passwords that use 26 letters and 10 digits. So six characters. So I'm looking at my password. Here's the password. I'm saying, how many passwords are there? Number of passwords, 26 letters, 10 digits, no restriction. Any arrangement of letters and digits and these 6 spots is valid. Can I think of that as a product rule? If I have no restrictions, I can see how many possibilities I have for the first spot, for the first location of the password, first character. Every possibility will work with every possibility for the second, right? Those are independent possibilities. I don't have to worry on the second character what I picked for the first character. There's no restriction. So those are independent choices. Later on you'll see this corresponds to a probability notion of independence. The fact that the first choice is independent of the second choice is the same as saying probabilities random variables are independent. Okay? So those are, every possibility, it's independent choices. So how many possibilities I have for the first spot? If there's 26 letters and 10 digits. 36 possibilities. How many for this one if they're independent? 36. 36. So how many possibilities total? How many passwords I have here? 36. The number of passwords is 36 times 36 times 36 times 36, which I can write concise as 36. That's an example of a Prologue rule. I counted these possibilities of password by saying I have 6 locations, they're independent. It comes down to how many choices I have for the first one, second one, third one. Since every choice is good with every choice, good with every choice, I could just multiply those choices. What if I say variation? Do not start with a digit. So that's a restriction. Not every possibility is valid anymore. I still have passwords, 6 spaces. I still have letters and digits, right? 10 digits and 26 letters. But I'm putting a constraint. You cannot start with a digit. You have to start with a letter. Then what? Somebody else. Yes. Somebody else. Yes.
Then for the first character, you have 26 choices.
Right. So I got 26 for the first spot because I can't use digits. The possibilities on the first spot are just the letters. That's 26 times 36, 36, so on and so forth. So total that will be what? 26 times
36.
All right. Okay, very good. So we got Cartesian product and the Prologue rule, and that applies to places that may not seem so Cartesian. There was a question here, how Cartesian things can be applied. There's an obvious Cartesian where the stuff comes in pairs or triplets, like coordinates, right? Or like couples in a wedding, you know, who's with who in here. That obviously comes as a natural pair. When I talk about password and spaces, would you think of Cartesian products? Not immediately, right? So that's the same kind of principle. This is a 6-plet. It's not a 2-plet or 3-plet. It's a 6-plet with 6 spaces. And without restrictions, it's effectively a Cartesian product of the same set. The set that I was multiplying here with itself in a Cartesian set, my set M, what was the set in here that I keep multiplying with itself to get the possibilities? A, B, C, D, da da da. And 0, 1, 2, up to 9, right? This is the set of 36 choices, and the number of passwords, it's effectively in set notation n times m times n times n, right? Because I had so many possibilities for the first one, 36 of them. Okay? Any questions? I'm sure this is very easy stuff, and I think most of you have seen this or related operations before. But you didn't call it Cartesian or you didn't call it a product. This is pretty simple stuff. How about do not start with digits and does not end with letter? I put two restrictions. Yes.
Then it would be 26 times 36 is the 4.
So I have in the middle, I have no restrictions in the four, and then the last one, so this is only letters, and this is only digits, so how many of them are there? Okay. How about does not end with a letter or with 0? So I'm saying cannot end with a letter, and it cannot end with 0. Then what? Yes?
That's at the end equals to 9.
That's a 9, because now I have only 9 possibilities for it. There's only 9 digits that are allowed at the end. Hands up, who's with me? Good. Okay, very good. So we've done Cartesian products. Here's another Cartesian product that's very important in set theory and mathematics. It's a very particular Cartesian product. So I got to set A, say it's 1, 2, 3 like before. And the set I want to define is the power set. It's called 2 to the 8. That's just a notation. Don't get scared. I'm not raising 2 at the set and then trying to figure out what it is. It's just a notation. This is the set of all subsets of A. So subsets we didn't define. I think you've heard of subsets before. Is any partial set. So a subset of A, which ones are those? I can have the whole set that is a subset. Even though it's not the proper subset, it's the whole set. We say this is included, this is sign, included in A. What's another subset? 1, 2 is a subset. What else can I do with 2 elements? So I get 1, 2, I can get 1, 3, I can get 2, 3. Those are also included in A as subsets. Can I get subsets of only one element?
Yes.
That'll be the 1, 2, and 3. Those are also subsets of A. And can I get a subset of 0 elements?
Yes.
Right. How do I call that? There's a notation for it. It's called empty set. That is a subset of any set. So how many subsets I have here for the set A? I have 8 subsets. So what I want to show you are Cartesian products that counts this in general. So we just count the subsets for a set with 3 elements. What if I start with A having 4 elements? 1, let's not call it 1, 2, 3 anymore, let's call it A, B, C, D. How many subsets with 0 elements? There's only the empty set, so that's 1. Subsets with 1 element. How many subsets can you generate with 1 element here? 4, right? Those would be A, B, C, and D, so there's 4. How many subsets with 2 elements? How many ways can you pick two elements in here in A, B, C, D? You can pick A, B, you can pick A, C, you can pick B, C, B, D. 6 of them, right? I'm not going to enumerate them, just A, B, B, C, so on and so forth. There's 6 of them. And I can have 3 element subsets. As in A, B, C, B, C, D, A, C, D, right? Things like A, B, C. How many of those I have?
4.
We have different numbers. So how many subsets of 3?
6. Oh,
I had 4, I heard 8, I heard 6.
right.
How many subsets of 3? How many ways can you pick 3?
4.
What's the easy way to think about this? If I am to pick 3, I have to leave on the table 1. So picking 3 is the same as leaving 1. So how many ways can I pick 1? Do we see this? This is the same mechanism. For any 1 you pick, you leave 3, or for every 3 you pick, you leave 1. Those are the same count, right? So there'll be 4 of them. And how many 4 element subset? It's 1. So total is what? 1, 4, 6, 4, 1. How much is that?
16.
Hmm?
16.
60. So for 4 elements, the power set, I think it has a notation. I honestly forgot a notation. I think it's something called like power set of A, something like that. Of A. Or sometimes it's called 2 to the A. Either notation is fine. It's all the subsets, including the set, including the empty set. What do you think is going to happen here? If I have 3 elements, I get 8 subsets. If I have 4 elements, I get 16 subsets. That's not an accident. How many elements are in the power set? How many subsets are there? Yes?
2 to the power of however many are in that.
Right. That's not an accidental notation, right? That's why they do 2 to the power, because the size of the power set, as a set, the size of it is the size of, this is the set, and it's 2 to the size of A. If A had 5 elements, how many subsets were going to be there? 32. And if A had 10 elements, how many subsets would be there? 10 to the 2 to the 10 is what? 1024. So I want to prove this theorem. The size of a power set is 2 raised to the power of how many elements are in the set. I'm going to do it with a Cartesian product, with the product rule. Here say, I'm trying to generate, just like with the passwords, I'm saying generate a subset or all subsets. Just like I looked in here at generating all the passwords, and I said, hey, I have so many possibilities for this spot, so many for this spot, so many for this spot, so many for this spot, and then I multiply them. For multiplication, I have to be worried about the fact that they're all valid. Any choice in the first spot works with every choice in the second spot, and so on and so forth. Therefore, this will work out. So I have these spots here. And I'm going to say, this is the first element of A, of my set. This is the second, third, and this is the, let's say, the A has K elements. This is the kth element. As a spot, the spot for the kth element. How many options, if I generate a subset, I want any combination of elements, any subset, that means I can have anybody in or not in. I could have any choice for an element, right? Like in here, there's subsets that contain the 2 and subsets that do not contain the 2. So how many options in generating subsets I have for the first element? If I think of a subset, I want to generate a subset. What can I do with the first element? How many options are there? Again, I'm not asking you pick a number, pick a value from A. If I ask you pick a value from A and has k values, how many ways you have to pick a value? So if I have 100 students here and I'm asking you pick a student, how many options are there? 100 options. But I'm not asking that question. I'm fixing a student, I'm calling him, and say I want to create a football team. Now I'm only looking at him. How many options I have regarding him in a football team?
On or not
Hmm?
on the team or not on the team.
I have only two options. He's either in the team or not in the team, right? My football team is a subset of people from the class that will play football, right? If I pick one particular element, there's only two options, either in the team or not in the team. So I'm counting all the options for how I create a football team or how do I generate subsets. If I fix an element, say that's this one here, how many options I have for that element when I think of subsets? Yes?
Can you use binomial theorem for this?
Yes, but that would be a circular thing because we need this for the binomial theorem. We'll get there next week. So how many options here? Is two, which I either include in subset or exclude. How many options I have here? Or possibilities. How many options I have here? So think about this set. How many sets have one in them? There's about half that have one and half that don't have one. That's easy to see. For every subset that has one, there is a corresponding subset that doesn't have the one. Right? If 1 and 2 is a subset containing 1, what's the corresponding subset that does not contain 1? Just the 2, right? So I have two options, two options, two options, two options. Now, is everyone valid with everyone? Every option I get here, with every option from here, with every option here, will generate a subset. Right? Because I have to worry about this validity. Every time I choose my hat and my jacket and my pants, is that a valid combination or valid sequence or set? So every choice is valid with every other choice. That means the number of possibilities, which is the number of subsets. Because every one of these choices generates a subset. If I say, choose this element, include, exclude, so on and so forth, that's a subset. The ones that I say include are in, and the ones that I say exclude are out. So how many subsets I get here? If I have 2 times 2 times 2 times 2. 2 to the k, which is 2 at the size of A. How can I generate the empty set? Empty set corresponds to what options? What exact options? Yes?
Exclude every,
How do I generate the whole set?
include every.
Right? So you can see for every particular exclude, include sequence here, I generate a subset. Sometimes the empty set, sometimes the full set. And every subset corresponds to include, exclude, right? Every time you look at a subset, you can tell which one has been included, which one has been excluded. So we just proved this theorem that says the number of subsets or possibilities of picking elements from a set is 2 to the how many elements are there. So here's another problem specific for computer science. If I have ASCII characters, right? You know how many things are, how much memory an ASCII character takes? 1 byte, right? 1 byte is how many bits? 8 bits. So how can I think of this that way? Well, I have 8 bits. Here they are, the bits. And because they're bits, what bits mean? What are the possibility for bits? 0 or 1. Every one of them is 0, 1, 0, 1, so on and so forth, 0, 1. So how many ASCII characters can I generate with 0, 1 bits if I have 8 of them? 2 to the 8. So if I represent anything on 8 bits, the number of possibilities is 2 to the 8. Same exact principle. I have 2 options for the first bit, 2 options for the second bit, 2 options for the third bit. The number of options, whatever you write characters, numbers, encoding, ciphers, anything you write, if it takes 8 bits, you have 256 possibilities, which is 2 to the 8. So 2 at the 8 is 256 possibilities. So if somebody asks you, hey, I have an alphabet of 300 characters, can I represent it in ASCII coordinate bits? No, you can't, because you only have 256 different arrangement of those 8 bits. You can't represent more than 256 things on it. All right. So about sets, sometimes this is called a bit vector notation. You're gonna hear that. It's just a fancy name for the same thing. I can write this set this way, and I can say, here's this elements are, this is 1, this is 2, this is a 3 in this set here, 1, 2, 3. Let's add 1, make it a 4. So A here is 1, 2, 3, 4. Sometimes a subset is just a bit representation, saying if I want, say, I want the subset 2 and 4, what that corresponds to as bits. I have to 0, 1, 0, 1. Suppose I want the subset 1, 3, and 4, what that corresponds to. 1, 0, 0, 1, 1. So when you hear bit representation of a set, then it's just saying put a 1 when you have the element, put a 0 when you don't, and that way you get a bit representation of the set. Do not confuse this with the notional orders. Sets, even though they're written in a certain order here, they don't have an order. The set 1, 2, 3, 4 is the same as the set 2, 3, 1, 4, the same as the set 3, 1, 2, 4, so on and so forth. This is the same exact set. I just pick an order to write it down. To me, to talk to you in class right now about this set, I need to put it in some order, right? I need to write it in an order down. But I could have chosen any order I wanted. The fact that I chose an order doesn't mean the set has its own order. It's just the order which I choose to write on the board. Maybe he here choose to write it down in a different order than I wrote on the board, which would be perfectly fine. Because sets don't have order. Just when we talk about them, we may write them in a different order. As opposed to sequences, 1, 2, 3, 4 a sequence, that's very different than 3, 1, 2, 4 as a sequence. So you're gonna hear about that. I'm sure a bunch of things that you know include union, intersection, right? So let's make sure we all know that. What's the union of A and B? Union. In here. What do I get for the union? Is everybody in A and everybody in B? How about this one here? Do I have to write it again? Do I put the one here or not?
Yes.
Yes or no? No. Union. Every element in either set written once. So in union, we don't put the elements that come from both sets together, right? So what about A union B union C? I can union 3 things. So it's just everything together. That's what it means. So that is 1, 2, 3, A, what else? B. How about in the intersection? Intersection. A intersect B, that is common. Common, also only once, of course. Sets don't have repeated elements. like graphs, unless we call them. For graphs to have multiple edges between 2 points, we have to call it. So how are we going to call a set if we really want multiple elements? Maybe. I don't know. Let's just say sets don't have repeated elements, to keep it simple for now. A intersect B is who?
1.
1. How about B intersect C? Is A, right? How about A intersect C? 1, 2, 3, A to B.
2.
Okay? Union and intersection. There's a picture that you can draw. Say here's A, and here's B, and where is the union? As a visual, where is the union in here? Everything, not the whole board.
Yeah, except
Everything in the circle.
So it's this, right? Everything is this. That's the union. This is union. And how about the intersection? Where's the intersection? This is the intersection? Nope, not this. Let's just do it with, it's easy to see. This stuff here is the intersection. So union is A union B, intersection is A intersect B. I think we're going to insist that you use this kind of notation, so don't write intersect in English. Use this U for union and backwards U for intersection. Since we're here, this has a name. Anybody knows the name for this round thingy is? Here's the elements. What?
Venn diagram.
Very good. Venn diagrams like this, double N. It's just a name, so we can call it pineapple. Don't get stuck with names, right? It's Venn diagram. Oh, you don't know what the Venn diagram is. You must be an idiot. That's not true. I don't know what the Venn diagram is. I got a PhD in mathematics, and when I taught this class first time, students told me, "Hey, what's Venn diagram?" I was like, "I have no clue." Oh, wait a minute. It's just drawing those bubbles with points in them. Don't get stuck with names. Mathematics is about reasoning and understanding why something happens. If somebody uses different terminology than you, doesn't make it smarter or less smarter. It's just a different name for the same thing. Okay. So draw those balls with elements. What about this side here? This side. Only this part, left side. What is this? What is this? Let's write it as a set builder notation. These are all the elements that are from A, and they're not in B. So actually, let's do all of them. These are all the elements that are in A and in B. That's the intersection. And the union, the whole thing is all the elements that are in A or. So in logic, if we don't say or, if we just say X in A, and then later on we say X in B, we mean both of them. We want them true, right? When we enumerate a bunch of properties, you know, I've been to the groceries, I cooked, and I ate, and then I fall asleep. I means I done all of them. When we say or, it means I've done one of them, not necessarily all of them. Maybe I've done more than one, but it's some of them I've done, right? So this is the whole thing. It's either A or B. The middle part is both in A and in B. This one is in A and not in B. And this one is X in B, but not in A. Again, there's an and in there. I'm not saying or. It's in B and not in A. So this is a set of X with that property. Now those two things also have names. We say union, intersection. This is difference, A minus B, some people call it A minus B, like in the real minus. This would be who? Oops. This would be B minus A or B minus A. Don't be surprised if you see the minus flat or curved, like a diagonal. Either way, it's fine. As long as it's clear you're talking about sets, not the set difference is not the same as the numerical difference, right? B minus A doesn't mean take an element from B, like a number, take one from A and make the difference between their values. That's not what it means. It means all the elements that are in B and are not in A. This part here. And there is even a more advanced one that says, I want the two sides without the middle. So how can I write that down? I want the two sides, but not the middle. So I want A minus B, right? That side. And that's union, right? Because they're on the other side too. B minus A. So I got this side and this side. It's called symmetric difference. Might be a sign for it. I think A triangle B. Again, that's just another name. It's the sides, the differences together. However, what I want to point out here, I could have written this differently. Instead of saying, I get the same side, I get this part in here and this part in here. Instead of saying it's the left and the right without the middle, how else can I say this? Get the same elements. Yes.
A, like, union with B.
Everything.
Yeah.
Right? So this is the same as everything
Minus A intersection B.
minus the middle part. So those two things kind of something you can get in the quiz. Like, why is this equal? Those two sets are equal. Whether you look at left side and right side, you get the same thing as you look like everything minus the middle.
If you wanted to prove that on a quiz, could you just draw the Venn diagram?
I don't know. Remember the 8-year-old thing test? I think the safest way for sets is to go, I mean, you can do this for yourself to see, okay, what is this problem even asking me? I need to put it on paper to see what they mean. And then it's going to be obvious what it means. But I think the easiest way to say, pick any element in here. Right? So the way the proof will go, I'm not going to do it here. That's an exercise. I'm going to pick an x in here. Any element that's in this or B minus A. And I'm going to do a bunch of math. Some steps, some inference, argument. And I'm going to end up with, okay, then x must be in here. X union B minus intersection. So I'm proving effectively everybody from here must be in here. Is that enough? What I just proved is what? I proved that the first one is a subset of the second one. I proved everybody from here, it's in here. Now I need to prove the other way. It's the second part. Any y that is in A union B minus A intersect B, again, we need some bunch of math. And then that has to come, okay, y is in A minus B union B minus A. So while this is not a proof, because clearly I skipped those steps, you can do those. In order to prove two sets are equal, usually the safest way is to take any element from here and show it's in the other one. And backwards, take element from here, show in the other one. Then they have the same elements.
Any, not all, right? Like,
Any and all in this sense means the same. Because you say any, you mean any one of the all.
okay.
Unless you mean all as the whole set, as an entity. All elements is not one of them, it's the whole set. Then it's a different entity. A set is not the same entity as the elements in the set. But in here, when you say for all, like the mathematical, you know that V with the bar? Yeah, that for all means for any. So it's saying any element you pick, it must be in the other one. That means every element you pick must be in the array. Who's with me so far? Question?
So is A minus B the same thing as A minus the intersection of A and B?
So that's, I think, go back to what he said. We draw this thing and check it out. What did he say? He's asking a question. I think that when you get such a question, the right way is to just draw it. You're saying A minus B is the same thing as A minus
the intersection of A and B.
Is that true? Like on a visual, where is A minus B? Is this semi-moon here, right? Where is A minus the intersection? Is it the same moon or not? Semi-moon. Yes. So visually it checks out, yes. But then how do you prove the thing? I think, again, the safest way is to say, everybody here, pick an element at random, any element from A minus B. How do I prove it's in here? What do I have to prove?
Put any element in that one.
So I say, okay, how do I prove this thing? Again, not a complete proof. Pick any element x in A minus B. We want, so sometimes when I say want in a proof, it doesn't mean I prove that. It means that's what I want to go. So you'll see in my math proofs, sometimes want something. That means this is what I want to get to the proof. Very useful to tell the reader that's the whole point of doing this. Not that you proved it already, but that's what you get. What do we want? We want to prove x in this, which means what? How do we prove x is in a difference? X has to be in A, and x has to not be in B. It's the intersection, because it's A minus something, so it has to not be in the intersection. So proving that every element here is in here means take an element and then show that two things. It's in A, and it's not in the intersection. Because if it's in the left side but not the right side, it's got to be in the difference. Make sense or not? There was another question before you. Yes?
Yeah. Could you have a set where you have a repeated value? Like, for example, if A was...
Unless we call it multiset, that's been discussed before. Unless we say multiset, we say simple sets, like in graphs, we cannot have repeated values. In sequences, we definitely can. 1, 2, 1, 2, 1, 2, that's a sequence. But in here, we have all the elements is written once. Yes?
So for that previous one you were discussing, you said you proved
This?
that one works too. How you can prove it in one direction, then you have to prove it the other way.
Right.
Can you prove it in one direction, then just prove the two sides are the same size? Would that also do it?
Yes.
Okay.
So, but you have to know a theorem to do that.
Okay.
Let's do that theorem. The theorem he just said is, here's how you prove two sets are equal. He's saying, if you prove A is a subset of B, right? This is called subset. And size of A is the size of B, that's what I understood that you're saying. They have the same number of elements. Then A must be equal B. He's saying it's enough to prove one side, it's a subset, and that they have the same number of elements. Is that true? Or false? We need another property to make it true. It's not true in general. Again, like I said, there's some concept here with infinite sets that you guys don't know yet. We're going to get there. How about n and z? Is n a subset of z?
Yes.
Is n has the same size as z? Yes. It's called the countable infinity. This is called countable infinity. Everything that's infinite, but it can be enumerated or counted. So they have the same size. According to the theorem, n equals z. Is that true? Obviously false. So what else we need in here? We need another property. to make this theorem work. They have to have a subset property, they have to have the same size, and finite. By the way, finite means their size is what? Finite means the size of the set is a natural number. Infinity is not a natural number. Finite means their set has to be 0 or 1 or 2 or 3 or 100 or 1,000,000 or 1,000,000,000, but not infinity. So with this property, then yes, the theorem stands. You have until tomorrow to prove it. That if I have two finite sets, one is a subset of the other, and they have the same size. Well, what else I need to prove here to make them equal? I already proved A subset of B, I know that. All I have to prove now is, see if that's difficult. This has a lot to do with those functions that I talked about before, one-to-one mappings. What this is saying, there is a one mapping from A to B that goes, every element goes into another element. The question is, why does it have to cover the whole B? Right? From N to Z, there is a mapping from N to the natural elements of Z, but not to the negative ones. So, how does that work for finite sets? Something to think about for the rest of the week. But this theorem is true, this way with finite sets. Let me enumerate a bunch of set in set builder notation just to make sure that everybody's got the point. So here's a set. All the x's with property x in z, and 0 smaller than x squared smaller than 10, which is the same set as saying x in z to start with, 0 smaller than x squared smaller than 10, which is the same set as saying x in z with x squared smaller than 10, right? Putting this 0 on this side doesn't do anything. Why is that? It's not a constraint. Whether you put the bigger than 0 or not doesn't affect things. Why is that? X squares are positives all the time, so we don't have to worry about x squared. So what is this set? What are the integers with square less than 10? What's the smallest one? -3, -2, -1, 0, 1, 2. So this is a set builder notation. Set builder gives a property, and everybody who has that property is in the set. This is enumeration, or iteration, or indexing. Actually, indexing, we're going to talk about it right now. Indexing is a counting method. Counting sets method. And it's very simple. If somebody show it to you, you'll be surprised how many problems seem complicated and you have no idea where to start it. And just by doing the right indexing of a set, you get the answer. For example, I want to count, here's a set A multiples of 5 between 100 and 200. This is kind of a set builder notation, but in English. I didn't write it mathematically. I mentioned the property, so I want the numbers that have this property, but how can I write this with math? I want all the x's in z, 100 smaller or equal than x smaller than 200, and what else do I need here in my property? Yes?
5 divides x.
I could write 5 divides x in number theory notation. So this is called divides. Or I could write like we did before, I could say x is 5k. It's a 5 times something. It's a multiple of 5. So now those two definitions mean the same thing, but one is in English and one is in math. And I can enumerate these numbers. I can write an enumeration here. What's the first number in this range divisible of 5? 100 maybe? What's the next one? 105. What's the next one? 110. And what's the last one? The next to last one? 995 and then 200, right? Here's how indexing works. What I mean by doing indexing. What I would like is to write those numbers in a way that I can easily count them by an index. So I'm going to write the same exact values, just with indexing in mind. I'm going to say, how about 5 times 1 plus, how much do I need to get 100 here?
95.
95. Then I get 5 times 2 plus 95. Right? 5 times 2 plus 95 is 105. Next one is 5 times 3 plus 95. Is that true? 5 times 95 is 110? Okay, what is 195? Is 5 times 20 plus 95. And the last one is 5 times 21 plus 95. How this helps me? Now, this is the same exact values. And I can even write it concise. I could say this is the set of 5k plus 95, right? With k from what range?
0 to 21.
Starts at 1 and ends at
21.
21. This set is the same set. It's 5k plus 95, where k is an integer, of course, between 1 and 21. So who's the index here? What variable is the index? Yes.
1, 2, 3.
This k. Right? This way, it's extremely easy to count this set. 1, 2, 3, 4, 5, 20, 21. How many elements are in here? 21 elements. Right? The size of this set, A, is 21 because there are 21 indices. Or the range of the index is 21. How about B is a multiples of 7 between 100 and 200. Same range. What are the multiples of 7? What's the first multiple of 7 between 100 and 200? 105. Next one? Next one? Add 7, right? And the multiple of 7 is that one you have plus 7. And the last one is? If I divide 200 by 7, how much? 196. If I want to index this set, this is 7. Let's say I start from 0 this time. I could start from 0 if I want to. 7 times 0 plus how much I need here? 105. The next one is 7 times 1 plus 105. The next one is 7 times 2 plus 105. Up to this 196 is 7 times what plus 105? 13. Very good. So now my indices, I can write it in index notation. It's 7k plus 105, where k ranges from 0 to 13, right? Because I started at 0 and I'm ending up at 13. How many indices are from 0 to 13, including 0, including 13? This is 14. The size of B is 14. The range of 0 to 13. 1 to 13 is 13 values, but I have 0 here, so that's 14 values. Indexing, well, very simple. It's quite powerful because it provides you a map, a one-to-one map between indices and the values. And then if you count the indices, you just counted the value. So the implicit one-to-one map here from indices which is k, to a values of a, is from k I get, is written here, 5k plus 95. Every index k leads to a value 5k plus 95, and every value is associated with an index. That's a one-to-one map. Therefore, how many indices you have corresponds to how many values you have in the set. How about set C multiples? How about say C A intersect B? That is, which values are both here and here, right? Here and here. So how can I write that? Well, this will be between 100 and 200. That's easy to see, because if A has the elements between 100 and 200, B has elements 100 and 200, the common elements must be between 100 and 200. But the common elements can be described in terms of number theory, like multiples of something. So they have to be multiples of 5 to be in set A, and they have to be multiple of 7 to be in set B. What does that mean in terms of number theory, divisibility, prime factors? They have to be somebody else. So if they multiples of 5 and of 7, yes?
Multiples of 35.
Multiples of 35. Is that, by the way, always true? If somebody is a multiple of some value x and some value y, it has to be a multiple of the product? No. So for example, 12 is a multiple of 6 and of 4, right? But it's not a multiple of 24. So there's some trick there. For 7 and 5 it works. If you want to be a multiple of 7 and a 5, you have to be a multiple of 35. We're going to prove that a few weeks from now when we get to prime numbers. But it's not the general rule. The numbers have to have a certain property. Anybody knows the property? Yes.
Greatest common denominator of 1.
Yeah, but I don't want to use all those words. For the two numbers 5 and 7 to have this property, multiple of 5 and a 7 equal multiple of the product, what has to happen between 5 and 7? Back. Yes, yeah.
Does it even also be prime?
Which means what?
They don't have any common factors.
They don't have any common factors. 5 and 7, there is no common factor. 6 and 4 in my previous example, they have common factors. That's why it doesn't work for 6 and 4. Anyway, so what are the multiples of 35? What's the first one? Maybe we should just enumerate those. 105, add 35 to it, is 140. Next one is 175. Is it done? Can I add another 35? No. So that's the intersection. And now suppose I'm going back to this picture here, and I want the union. Can I just say the size of the union is the size of the first set plus the size of the second set? No. Why?
Minus.
I counted this stuff twice. So I have to take out the intersection, right? Because it's counted twice. So if I want the union here, in this problem I do numbers. What the union means in this problem. A union B will be between 100 and 200, of course, because everything is 100 and 200 in this problem, will be multiples. How do I write that? Multiples of either 5 or 7. So instead of doing that, which is difficult, because if I enumerate that, indexing will be difficult. It doesn't, the reason for it is it doesn't jump nicely like this one jumps from every 5, right? The way I index this is every 5, 5, 5. This one is every 7, 7, 7. Now that one will not gonna jump like that. The first one is 100, then 105, then 110, then 112. So it jumps by 2, by 5. I can't do really easy indexing on this problem. So if I want to know how many numbers are here, I need to use this counting method. I already counted A. How many elements were in A? 21. and I counted B, how many elements were in B? Remember?
14.
14. And I already counted the intersection, which is the multiples of 35. How many were those? So what is this? 32? This is a very important theorem in mathematics, which you just said you can prove it, I think, by saying you want all the elements exactly once, that's the union, you take the ones in A, you take the ones in B, and you subtract the intersection ones because you count them twice. How does it work for 3 sets? The same thing. How does this stuff work for 3 sets? So here's I have 3 sets. A, B, and C, and I want the union, the count in the union. A, union B, union C, count. I want a formula like that, and I'm going to start like that. I'm going to say, well, it's everybody in A, plus everybody in B, plus everybody in C. Remember, those are counts, how many things are. But then like in there, I'm going to say, what happened is, the intersection between A and B, I counted twice. Because I counted this, every element in here is counted for A and for B. So I have to take that intersection out, and I have to take the intersection of A and C out for the same reason, and I have to take the intersection of B and C out because all these things have been counted twice. This I counted for A and B, counted for A and C, counted for B and C. So this is the same exact principle like with 2 sets. But now in here we have one more problem. What about this part in here? How many times I've counted the middle? I counted with plus sign for A, for B, and for C. So every element in here has been counted 3 times. And how many times I take it out, every element for here?
3 times.
I counted 3 times and I take it out 3 times. So what do I have to do?
You have to add.
Add it once. That's the intersection of all 3, right? So I need you guys to spend some time on this picture. Is it really the count of everything, the union, A plus B plus C minus the intersection of 2, 2, 2, plus add back the intersection of all 3? And if that's true, how it works for 4 sets or 5? This has a name. It's called Inclusion, Exclusion Principle. And to prove it, we need binomial theorem and combinatorics. So we're going to prove it about next Tuesday or so. We have to get some more math to prove it.
Is A union B union C the same as A union B and then union C?
Yes. If I want all the elements, I could do A union B and then union C, or I could do A union B union C, and so on and so forth.
So we could just plug in the formula for A union B and then union C.
Right. You can maybe do it mechanically by saying, I already know A union B from here, that's what you mean, and then see if it works out. But then how does it work for 4 or for 5? It gets messy. Induction, not allowed yet, okay? Good. So that's the inclusion-exclusion principle, and it's a very important case of it. Very important case. So I want to make a big, big deal out of this case. It's inclusion-exclusion, just a particular case. No intersection. In other words, every A intersect B is empty, every B intersect C is empty, etc. What is this formula becomes if all intersections are empty? The size of A union B union C is who?
A plus B plus
Just
C.
size of A plus size of B plus size of C. This is called the sum rule. You use this all the time already, since primary school. When you say, I have to deal with these students in here, and I'm going to deal with this group first, and then the next recitation group, the other group first, and the other groups. That was a sum rule right there. We're saying these groups are disjoint. This means disjoint. No intersection. It's just another name for saying no intersection. If I have disjoint groups, the number of students I have in my class is the sum of the recitation groups. Why is that? Because between the recitation groups, there is no overlap or intersection. So the sum rule works to say, this problem has 17 cases. Now I'm dealing with cases 1, 2, 3, 4. Then I'm dealing with cases 6, 7, 8. That's okay. Make sure you control that overlap, because if you have overlap, you have to use the main formula. This formula works everywhere. If you don't have overlap, you can just use the sum and other. Right? So for example, how many passwords starts with 1 or with 2? Can I say, I have passwords of 6 digits, and like we discussed on the board, and they have to start with a digit. So I'm splitting them into passwords that start with 1, passwords that start with 2, password that starts with 3, 4, 5. How many classes I have? 10 classes, right? Because 0, 1, 2, 10. Are those classes disjoint? Can a password start with 1 and with 3 or with 5 in the same time? No. So to count all these passwords, I just count each class separately. Now I have to say one more thing, which you already know for the homework. It's called Pigeonhole Principle. If I have 120 students, 21 students, I think I already said this, into 6 groups. That's are the recitation groups. One group has to have at least what? 121 divided by 6. Now you should transform that into an integer, right? If it's one group has at least 121 by 6, that really means how many? 21 students. How about one group has at most, can I do that inference too? 121 students to 6 groups. There is at least one group that's at most 121 by 6. Is that true? Can I say, if there's 121 students in 6 recitation groups, one of these groups has to be at least this as integer, that's got to be 21, right? Because if it's more than 20, it's 21, and this is at most that is 20. This is called the ceiling and the floor of the two values. Ceiling is rounded up, floor is rounded down. So now why are both of them true? They're going to tell you things with pigeons and holes and cages and all that. Ignore. Ignore. That's not the right way to think about it, because you get so confused with those pigeons that you just, you should, in this kind of problem, consider the alternative. If this is not true, all groups have to be 20 or less. I can't get to 121. If this is not true, all groups have to be 21 or more. That's too many. This is too few, that's too many. So in these kind of problems, ignore the pigeons and instead say the alternative is impossible, because that'll be too many or too few. So I'll see you tomorrow and Thursday.